Okay, today we want to talk about making a temperature probe for a digital multimeter like this one right here. And basically, it doesn't require very much for it. It works with any of them because they have ohms measurement, and that's what you use to measure the thermistor. The thing is, you might think it's too hard to figure out the temperature from the resistance on it, but it's not that hard actually. See, what it is the temperature is linear. It's linear, but it's not the actual temperature number being linear. It has some math to it before it becomes linear. But anyway, I made a JavaScript calculator online that works with get on the camera here, this temperature probe. And it works pretty well. You have to calibrate it at first, but I'll go over the steps of calibrating it in a few minutes. But anyway, you don't have to calibrate it if you use one I got. By the same one, there's no need to calibrate it because it'll be exactly the same. You may want to calibrate. You can calibrate it if you want to be more precision on it, but maybe where it's more accurate, because it will be a little bit inaccurate when it's not the exact same one. But that's okay. It's not going to be off that much. Now here's what it looks like. You know this formula here, y equals ax plus b. That's a is your slope and b is your y-intercept. Well, it looks like that, but except you got to change it around a little bit. You got to put 1 over a times natural log of x, which is your resistance, plus b is your slope, and your y will be your temperature. That's how you figure it out. And there it is over there showing you how to hook it up. Your thermistor. Anyway, here's the features. Works with any multimeter. That's pretty good. Easy to build. Easy math to calculate temperature. And the best, especially, no power supply or battery required. See, because it uses the meter's power, that signal that goes through to measure the resistance of it. It doesn't. That's all it needs. Since it is resistance that varies from temperature to temperature. Now this here is a graph showing you of NTC thermistors. As you go, as the temperature goes up, the resistance goes down. So it'll be like this. It'd be the other way around, going like this if it was PTC instead of NTC. What that means is negative to temperature coefficient, and PTC stands for positive temperature coefficient. Anyway, I'll go over the steps where you can download the JavaScript page and edit it to make it work with your thermistor, and how to do linear regression with it. Linear regression, you'll be able to find it on if you have a graphing calculator, it's on there. Usually graphing calculators will have linear regression. You won't be able to find linear regression on a standard non-scientific calculator, but if you have like a regular scientific calculator like this one right here, it has linear regression on it. Now some of them might say ax plus b or a plus bx. Those two formulas are the same. The only thing is the written different. They're written in a different way. And some calculators have both, like the TI-83 does. We'll have the ax plus b and a plus bx. It's just the same way of writing it, a different way. Now I'll show you how to copy it. It's really easy. Well, I'll show you how to get into the JavaScript code and make it where it works with your thermistor. Now, when you do that, you must take these times 10 to the minus 4. It has to be e to the e minus 4, and right here it has to be e minus 4 there. The more digits you have, the more accurate it's going to be, but it basically, it's all accurate it's going to get. It doesn't have to have all the digits. But more digits, the accurate it will be. So, I'm going to show you how to use it. There's linear regression on this calculator right here. Go in here, turn it on. Go to mode, go to stat. Statistics mode is what you want to go to, because since this is a statistic function it uses. And there it is, A to hit 2, get A plus BX, which is on this calculator. And it gives you these in there. And I'll show you how you enter them in. It's kind of tricky because it do a little bit more math to the number you enter in. And you can't enter it in just as that number you get on the meter and on the food thermometer. But it's very easy to figure out. Thing is, you have to know what it might be easy to think about it as. Let's talk about the formulas in what's it called? Fahrenheit and Celsius to kelvins. Since you have to convert to kelvins, since this formula only works with kelvins as a temperature measurement, it will not work with Fahrenheit or Celsius. You have to convert it to that. You can still use Fahrenheit, Celsius. You can probably write that program like I did on mine, because you convert kelvins to Celsius and Fahrenheit, which it does. So it makes life a lot easier of reading it. Thing is, you get a meter like this that has it on there, it usually doesn't have both temperatures. And it's more expensive also because of it. But I'm going to show you erase some of this. I'm going to show you the formulas you'll need to know in order to convert it to, well, we're going to convert Fahrenheit, but since food thermometers measure in Fahrenheit, we're going to use Fahrenheit as our type of measurement that will convert to Celsius, not Celsius, to kelvins. Okay, I'll write down the formula. Okay, here it is. Here is the formula to convert kelvins, Fahrenheit to kelvins. What you do is you take the K, which is kelvins, equals 5/9, then times it by parentheses the temperature plus 459.67. Then when you get done with that, you must enter into the calculator. And how you enter into the calculator, you have to do 1 over the kelvins. Since that's how they're linear on the graph is when the 1 over it, or 1 over the kelvin's temperature, it must be done like that. And that's how it works. Now we're going to we're gonna show you how it works. See, I have the meter right here hooked up to it. It has, right now it says 65 kiloohms. It's 50 kiloohms. But why is it 65? It's colder in here, so the resistance went up a lot. And here is the temperature probe. So now, I'm going to do is show you how to calibrate it. It's very simple and easy. It might take a little while because you have to enter these formulas, and so what you should probably do is for the Kelvin one, since it's probably hard to memorize, write down the Kelvin formula, which is 5/9 times, in parentheses, temperature of Fahrenheit plus 459.67 in parentheses. And that there will give you your temperature in kelvins, which is needed. And then after that, you must do that. You can probably do it all in one shot on the calculator. And this calculator lets you enter formulas into the table, so it will actually work easily with this calculator. Now some of I see don't have a table, and you have to, what you have to do is you have to enter the x and y's values as they go. As you go enter x in and then enter the y in, one at a time. So now what I'm going to do is we're going to go out there and we're going to look at how to calibrate it. Okay. We got the calculator here, we got the formula written down. Now first things first, the first one we know is the room temperature. The room temperature of what the thermistor is weighted for. It's like 50 kiloohms. So put natural log of 50 kiloohms. That'll be our x value. And since the room temperature is typically 70 degrees Celsius, we'll enter in this formula here, we'll place T of 70. So it will be 5/9 times, in parentheses, make sure we put 1 over it first. $70 plus 459.67. There it is. Entered it into there. There's your temperature right there. The next thing you have to do is enter another one in. Now, it may be tricky to get heat off it, but I found a way. What we'll do is put a glass of water into the microwave, take it out, and measure its temperature with the food temperature and also with the thermistor. That will give you the temperature that's known on the food temperature thermometer probe, and also will give you don't so you know what the resistance is at that temperature. Since you have to have for linear regression to work, you have to have at least 2 points available typed in. It's good to go with more because then it becomes more accurate. So let's go ahead and do that. Hey, the food thermometer here, we'll turn it on. Okay, put it in here. We're getting about 72 degrees. 80, 90, it's going up. It hasn't made its decision yet. 98 degrees. Okay, place the dimensional probe in there. Look what we get. We get that 17, 110 degrees. So it's 100. So it's 17, 18.4, 113 degrees. Okay, now what we might want to do now is putting the resistance in, so we do logarithm the natural log of 18,000. Enter that in, and then on the y value you enter in the temperature, do the reciprocal of the temperature. So it'll be 116. Well, it's in Fahrenheit. It's Fahrenheit, so it's doing in kelvins. So you put one over, and make sure to do that first, otherwise it won't come out right. 5 over 9 times in parentheses 116.8 plus 459.67 entered in. There we go. Now you might want to check to see if you're doing it right. Now how you can check is well, if you do the regression on a TI-83 or 83 calculator, it will have it'll automatically tell you what the coefficient, the coefficient of it, telling you how correct it is, how accurate it is. We can go in here and hit that 5D, hit enter with the R variable, and wait, no, we get a perfect. Can't see that on there. You get a perfect linear formula, because it's 1. I believe it'll be negative number if we were using PTC Demister. If you want to try it, let's try it out. Let's try putting in the natural log of 50,000 ohms. Put this in parentheses, so you have to do the 1 over it and then put it. How to do this? I have to take that. Hit this there. 5. Hit the Y. That tells it to do Y. Those 5 functions different on the TI-83. It's you guys actual function for it, instead of like acting like a variable. And that's pretty good. For room temperature, I think it comes around 294 degrees Kelvin, which is correct. And if you check it out on there, you can see that it's 294 kelvins. Now let's try to get it more accurate. Let's put on the microwave for a little bit longer and see how much heat it generates for it to measure it. So we have more than just two different type of temperatures entered in. So let's try that. Okay. Just started something taking it out of the microwave, and here's what its temperature is. It's 107 degrees. And if you look at meters, it's 25.4 kilohms. Okay, let's put that in here. Natural log of 25,400. And temperature is 100. We got to do it in Kelvin. Over 9 in parentheses times temperature 107. Let's go on. Plus 459.67. Put parentheses around it. Parentheses, and we'll do the inverse of it, which is just probably a waste of power to make one. Same thing as divided by one. One divided by it.
But if I want to go wash the van.
Okay, got a minute in there. Let's see what it comes up to. We'll take what we got now. We got 26.4. 26. We gotta do the log and show log of. Actually, what we're gonna do is enter into the computer. Let's go. Now we're here. This link will be in the description. In the description will be a link to this page on my form, which will have the calculator right there, the JavaScript calculator right there, and have the source code down here. Down there will be our source code. Now you want if you're not using the same thermistor, you want the source code because you need to change some stuff into it. So we'll click that, copy, and we'll put it in Notepad. Zoom in. There we go. Then we have our slope and y-intercept. These are the two things we want to change. This one and this one on it. And what we're change it to is your slope and from the regression. Turn the light on in here. Still a little bit too dark. Okay, it was a setting I changed when I zoomed in. Anyway, let's get to the thing. First thing on this calculator, it'll be different for different calculators. TI-83 to TI-83 Texas Instruments A3 Type Series Plus or whatever Type 1 you use will have the regression variables you need. After you calculate the regression, we'll have it there. You don't have to have a calculator. You can go to the internet and do the regression. In fact, since I want to make it that simple, I'm not going to use the calculator for that. We'll just enter it into here. You do it on a calculator or you can do it on a regression. I'm going to show you how to do it here. Linear and spell. There you go. And then right here, enter your X and Y values in. Well, I'll just transfer the ones I got on the calculator here onto here. You could use this doing it. You don't have to have a calculator. We could have did it this way in the beginning. Zoom in here. Zoom in. It's probably how good it's gonna go. X is 10.819778828, comma 3.39. Here we go, got them all entered in. And just click submit down here, see what happens. Almost entered 5 of them. No, I can do less than that. Let's try this site. Sorry about that. Okay, entered them all in. We got down here our equation, y equals 2.7. This here, since it's right by the x, as you can see, this here will go into our slope. Since this is after the plus sign, this will go to the y-intercept variable. So let's do that. And then since it says 10 there, you can't have 10 minus 10 or times 10 or whatever it says right there. You have to have you have to have the E symbol, which is what we're going to put in. I'll just copy paste it and change it once I get pasted in. Just watch. See now, once I go over here, change art, variable right here, zoom in on that. Change the center of that symbol there to put E. So slope. Oops. Okay, we'll just take that out, put it on the slopes. Our y-intercept right there. Change those symbols there for the 10 times there, because it probably will give a syntax error if you try wanting it on leaving it there. So you have to change it. But make sure after you put make sure that after when you get done with the inner numbers, make sure you have a semicolon at the end of it, like that, on each line. I'll just save it. We'll name it Mr. HTML. Open it up now. Now watch, if I enter 50 kilo ohms, since that's our maximum, bingo, we get 71.3224829916354 there. See, it works. Now let's try entering in, what do you say, 26? Point. And remember, in this box it in kilo ohms. 9 ohms. It'll say kilo ohms at the end of it to remind you to put in right or value range. there you have it. There you go. You got a simple way to measure temperatures. Well, thanks for watching. Hope you like it.